Good morning, students. Uh, in today's session, we'll discuss about the 8-point FFT derivation. The objective is 8-point FFT. This is n is equal to 8-point FFT derivation. So, before solving the problem using FFT computation, so what are the difficulties of DFT? Then why we go for fast Fourier transform computation to reduce the computations, direct computations of DFT. So in the direct computations, it requires large number of multiplication, addition and trigonometric functions. So in real time it is not possible to handle large number of samples. Okay, for n-point DFT it requires n square multiplications and n into n minus additions. So the DFT expression, so for DFT computation the FFT was developed to reduce the computation. So it can be performed either in decimation in time FFT and decimation in frequency FFT. So all the fundamentals concepts we explained in the previous session. What is the DFT equation? So the DFT equation, x of k is equal to the summation of n equal to 0 to n minus 1 x of n into w power nk. So this is the DFT equation. In this DFT equation, last session we discussed about the complete what is W, the twiddle factor. The twiddle factor. Okay. So because of this twiddle factor, symmetry of the twiddle factor W power kn. So what is W is equal to e power minus j 2 pi by n. So this is the twiddle factor e power minus j 2 pi by n. Because of the circular symmetry, because of the symmetry property, the two properties of DFT, important properties of DFT, out of so many properties, the periodicity property and the symmetry property is the FFT. This twiddle factor possesses a circular symmetry. Okay. So the periodicity property and the symmetry property reduces the most of the number of computations required for calculating the DFT sampled values. So the two algorithms, the symmetry property, so I think no need to explain again about the symmetry and periodicity property. Otherwise, we can we can write only the formula, the proof and all already we discussed. So the periodicity properties, you know that W power k plus n, okay, which is equal to W n k. So what is the, because the Wkn possesses this term possesses circular symmetry, and also W power k plus W of k of n plus n repeats periodically with the period n. It repeats periodicity property. It repeats periodically with the period. Say periodicity. Periodically it repeats with the period n. The other property w power k plus n by 2 which is equal to minus w power k. So this is also another important property. So the proof and all we have seen in the last session. Now in this session we will concentrate the decimation in time and decimation frequency FFT algorithms derivation in detail. Okay, so what are the two algorithms? The two FFT algorithms are decimation in time, in which we decimate, or decimation means divide. Okay, divide the time factor n. The first second algorithm, decimation in frequency FFT. This is because the FFT you can perform either by decimation in time or decimation in frequency FFT. In decimation in frequency, in which we decimate the frequency term. This is a time factor n. The frequency term k. Okay, this is a k, frequency term k, time factor n, and the frequency factor term k. Okay, in that equation. So in that equation, so this is a time factor, this is the frequency term. Okay, so this algorithms, this FFT algorithms is based on, so this is a general concept, is based on radix, or base. Radix or you can say is a base, based on radix or base on which the algorithm is developed. The FFT algorithm is developed. So in such algorithms, the number of samples n, and number of samples and the base r based on radix or base, you can say, or base r related by the equation n is equal to r power m. M is equal to 1, 2, 3. Example, if you take r is equal to 2, we used to say the popular radix, this is r, base, radix or base r, radix r. So we used to say radix to FFT. Okay, so now n is equal to 2 power m. So for example, if m is equal to 3, then we will get n is equal to 2 power 3, which is equal to 8 point. So now how you can pronounce 8 point radix to FFT algorithm. Okay, 8 point radix to FFT algorithm. If r is equal to 4, this is r is equal to 2, r is equal to 4, we have radix 4 FFT. So n is equal to 4 per m. If m equal to 2, we have 16 point radix 4 FFT we have to say. Okay, so what is the relationship between the number of points can be, what is this is important. N is equal to r power m. The r may be radix 2, r may be radix 2 or radix 4 algorithm. So that to reduce the time required for the DFT only with the FFT is developed. So decimation in time and decimation in frequency. Now you can classify into now decimation in time radix 2 FFT algorithm. Similarly, the radix decimation in time in frequency radix 2 FFT algorithm. Now we will see the derivation. As we said, how the samples, the n point is divided into n by 2 to n by 2 points. The input samples are divided into even sample and odd sample. Again this divided into further divided into in a similar way 4 n by 4 points. 4 n by 4 points. So n by 4 n by 4. So example n is equal to 8, so it will be 4.4 point, then it will be 2.2 point. So you have to divide the decomposition until you get 2 point DFTs are available. The bigger DFTs are decomposed into smaller DFTs until the decomposition process will continue until the 2 point DFTs are obtained. So this symmetry property reduces the number of computations required. So now, how the samples, the x of n samples, x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7 is divided into even and odd samples with respect to the position. So it will be x of 0, x of 2, x of 4, x of 6. Again it will be x of 1, x of 3, x of 5, x of 7. So again this will be divided into with respect to the position x of 0 and x of 4, x of 2 and x of 6. Again this will be divided into x of 1 and x of 5, x of 3 and x of 7. So it will be decomposed into odd and even, odd and even. So with respect to the derivation, the algorithm, how it was decomposed. So what is the general equation? X of k, now x of k is equal to the summation of n equal to 0 to n minus 1 x of n into, generally the w per, will takes direct equation w per k n. So now we are dividing this x of k which is equal to 2 even and odd parts. So we are dividing this n sequence into n by 2 first half. So summation of n equal to 0 to n by 2 minus 1 x of 2n and w power 2kn 2n even sequence. You will get even sequence 0 2, next time 1 means 2, 2 means 4, 3 means 8. For example, this will become n equal to 0 to n is equal to 8. No, 8 by 2, 4 minus 1, 3. So this will be x of 2n to w 2n 2kn w 2kn plus the summation of n equal to R and even sequence n by 2 minus 1 x of 2n plus 1 into w power 2n plus 1 into k. Okay, so if you substitute, you will get x of 0, okay, x of 0 sequence and 1 means x of 2 sequence will be there, x of 2 is if you apply 4, then x of 3 means 6. So these samples are divided into even and odd samples with respect to the position. This is a even term, we can say this is a even term, this is a odd term. So now we can split this part as, if you see the second part, okay, this w per k, this you can take this one w per k, then n equal to 0 to n by 2 minus 1 x of 2n plus 1 into w per 2kn, w per 2kn. So you can, now this is even function, this is even function, or we can say this is even function plus this w power k. How it is decomposed? Okay, this end point is decomposed into 2 n by 2. This end point is decomposed into 2 n by 2. So n is equal to 8. Now 4 point and 4 point. So this is 4 point and this is 4 point. So plus w per k into your odd function, let it be okay. So x of 2n sequence will be, you will get x of 0, x of 2, x of 4, x of 6 up to you will get x of n minus 2. Similarly here the x of 2n plus 1, you will get x of 1, n 0 means x of 1 you will get, then x of 3 you will get, x of 5 will get, x of 3 means 3 2 are 6, x of 7 you will get, up to x of n minus 1 you will get. So we are splitting the sequence into odd and even. So now see, although it needs to be evaluated n times, for k vary from 0 to n minus 1, k vary from 0 to n minus 1, each summation needs to be computed only n by 2 times for k varying from 0 to n by 2 minus 1, because the even term and the odd term are repetitive with the interval of n by 2. That is due to the periodicity property. The original DFT time is reduced by approximately 50%. Okay. Further, you can note that because of the symmetry property, the k value restricting to vary from 0 to because of the symmetry 0 to n by 2 minus 1. So you can write the symmetry property for k varying from x of k is equal to this ek plus w power k into okay. So k also varying from, that is why due to the symmetry property, k of, we know that n by 2 plus k to the range 0 to n by 2 minus 1. So in this case it will be ek minus w per k into ok. So for k equal to, because the symmetry property, w power n by 2 plus k, which is equal to minus wk. So because of this symmetry property, no doubt. Okay, so n by 2 plus k, so it will be symmetry power minus wk. So that you can write, use this one, x of n by 2 plus k will be minus w per k ok. So now this ok again, okay, can be divided into two parts, odd and even. Again this will be divided into two parts, odd and even. W per, so we can 0 to n minus 1. Okay, so apply the same decomposition theorem, apply the same decomposition, you divide this 2, so n is divided into n by 2 and n by 2 again. Now again you divide n by 4 into n by 4, n by 4 into n by 4 again. So now this ek will be, ek is equal to, this is divided into the summation of n is equal to 0 to, now to n by 4, this even term, n by 4 minus 1 into x of 4n to w power 4nk plus the summation of n equal to 0 to, again second part, odd and even, n by 4 minus 1 x of 4n plus 2 into w power 4n plus 2 into k. Now this term is even term, even of even term, you can say. This term you can separate the terms, w2k, w power 2k and the even of odd function. Okay, even of even and plus w per 2k into even of odd function. Now what are the sequences we'll get now? X of 4n means what? N equal to 0 to, so n by 4, 8 by 4, so it which will be equal to 8 by 4, 2 minus 1. Okay, so you will get n equal to 0 means x of 0, you will get x of 4 out of x0, x2, x4, x6. This even part now with respect to the position 0 and 2 only. So x of 0 and x of 2 only. Here next term x of 2 and x of 6 only. Odd and even function, x of 0, x of 4, then you will get up to x of n minus 4. Then x of 4n plus 2, this part, n by 4 means 8 by 4, 2 minus 1, 1. If it is 0, 0. If it is 1, x of 4. X of 4n plus 2 sequence will be now, okay, this one. 0 means x of 2, 1 means x of 6, like that it will go up to x of n minus 2. So this n is incremented from, the n is incremented from from 0 to n by 4 minus 1. This is the n value. Similarly, this is a even of even, even of odd. Similarly, the second term DFT odd sequence. Second term is odd sequence, is divided into W per K of OK. Even term and the odd term. We'll take this equation. So W per K odd term. Again this will be divided into n equal to 0 to n by 4 minus 1. So this is x of 4n plus 1, 4n plus 1, and W power 4n plus 1 into k, and plus the summation of n equal to 0 to n by 4 minus 1, x of 4n plus 3, 4n plus 3, 4n plus 3, W par 4n plus 3 into k. So now what is x of 4n plus 1? You will get even of original order sequence. So that is x of 1 and x of 5, like that will go up to x of n minus 3, and x of 4n plus 3 becomes, you will get the even of the odd of original odd sequence. So x of 3, x of 7 will go up to x of n minus 1. So you now divide in the derivation, divide both sides by wk. Okay, wk. If you divide by wk, then the equation becomes, the wk will be wk cancel. Okay, so divide both sides by wk. So it will be cancelled now. So you will get OK is equal to, this OK is equal to summation of n equal to 0 to n by 4 minus 1, x of 4n plus 1, W power 4nk plus W power, so if you see there, W power by wk, okay, 4n. So if you divide this one, you will get W power 2k. You will get W power 2k, the summation of n equal to 0 to n by 4 minus 1, x of 4n plus 3 into W power 4nk. 4nk. W power only 4nk. So only 3k divided by 2k, so you will get W per k, you will get only W per 2k. Okay, this will be, so this part. So like this you can decompose, so this is actually even of original odd sequence, then odd of the original odd sequence. This is even of the original even of the original odd, this is odd of the original odd sequence. So if you draw the structure butterfly, so the input pair and the output pair you can write, so the you can these are the, so you can implementation of the equation, will take the implementation of equation, the 8-point DFT, 8-point DFT butterfly structure, butterfly diagram. Actually this here the theory concept I'll try to explain. In computing endpoint here, so each the decomposition will continue. For example, the previous one k. So what is the range? So OK is equal to, you can write, so the continuation of the previous one, OK is equal to odd of even plus W per 2k into odd of odd sequence, you can write like this. Okay, so we'll structure we will see later. Okay, we continue the derivation. So OK is equal to odd of even sequence W by 2k into odd of odd sequence. So in a similar way you can, now the symmetry property, you can write W par 2 of n by 4 plus k, okay, which is equal to minus W par 2k, n by 4, the symmetry property. So the k range from, now the k range from 0 to n by 4 minus 1. So now this n by 4 minus 1 can be written in two parts. So now Ek is equal to even of Ek plus W par 2k into even of odd function. The second one, same, the k value ranges from, varies from, there is a n by 4 plus k can be written as even of even minus W par 2k even of odd function. Okay, so similar way you can write the odd function, OK is equal to odd of even function plus W2k into odd of odd function. Again, if the k varies, this is the symmetry property, which is equal to odd of even function and minus W2k into odd of odd function for k is equal to 0, 1, 2 up to n by 4 minus 1. So minus W2k, k is equal to n by 2 minus 1, this one. So for this, k is range from n by 4 minus 1. So this decomposition can be applied again. Okay, this decomposition can be applied. So this decomposition this decomposition technique can be applied again to divide 4 n by 4 point DFTs. It is into 8 n by 8 points. So this will continue. So normally you have to continue the decomposition until the decomposition or decimation, decomposition or decimation, or that is a divide until 2-point DFTs obtained. So this is the algorithm, but here this is a decimation in time FFT algorithm derivation. Radix 2, this is radix 2, decimation in time FFT algorithm. So decimation in time means the time factor is n. We are decimating the time factor n. Okay. If you similar way, if you decimate okay, the frequency factor k, then it is called decimation in frequency algorithm. In DIT FFT algorithm, you are decimating the frequency factor, the frequency term k. So this is called decimation frequency FFT algorithm and decimation in time algorithm. Okay. So generally the until 2-point DFTs. Now the 2-point DFT, how to draw the 2-point DFT diagram. Each decomposition stage doubles the number of DFTs. Note these are the points in 2 marks or MCQ or 4 points you can expect. Each decomposition stage doubles the number of separate DFTs. So for example n, okay, doubles the number of separate DFTs but halves the number of points per DFT, For example, see calculation computation n-point DFT. In n-point DFT with n is equal to 2 power y. Y is a positive integer. This decimation process can be repeated. So for n-point DFT, n is equal to 8. Okay, the decimation process repeated. How many stages? Repeated y times. What is y? So y, or you can say, so this is y, or you can say log n to the base 2 times. So this n is equal to 8. So log, okay, n is 8, 2, you can write log 2 power 3. So you can, which is equal to 3, which is equal to 3 times. Okay, so y is equal to 3 times. The decomposition is 3 times, 3 stages. N by 2, n by 2, second stage, again it is n by 4, n by 4, this is n by 4 and this is n by 4. 8 point, 4 point, 2 point. So how many times? 2 4s 8. Okay. So this basic computation, so this 2 point representation, butterfly representation, the basic 2 point, okay, representation, the basic computation of 2 point butterfly structure, because it looks like a butterfly. So the basic 2 point basic butterfly, since it looks like butterfly structure, butterfly computation. AB, this is a 12 factor. If you notice in the derivation, okay, the 12 factors, the will come with the odd functions. Okay, so this butterfly structure, so A is equal to A plus Wn to B, and this minus 1, B is equal to A minus NB. A minus. So this basic computation is performed at every stage. So which will take two complex numbers. So these two complex numbers A comma B, multiply B by the Wn per R, you can say. Okay, and then add and subtract, okay, to the product. Then it will produce the two new complex numbers A and B, the two complex numbers A comma B. So this is the basic computation, is called butterfly, because the flow graph resembles, looks like butterfly. So in general, each butterfly, in general, each, note down, it looks like a, in general, each butterfly involves one complex multiplication, okay, one complex multiplication and two complex additions. Okay, for n is equal to 2 power m, there are n by 2 butterflies. If n is equal to 8, okay, n by 2 is equal to 4, or you can say 0.5, this is 1 by 2, 0.5 n, 0.5 n, n by 2, or you can say n by 2, or you can say 0.5 n, which is equal to here 4 butterflies per stage. per stage. Per stage, how many butterflies are required? For n is equal to 8, n by 2 or 0.5 n butterflies. This n by 2 butterflies per stage of the computation. So, how many stages it requires? So, m is equal to, that is a log n to the base 2. How many stages? M is equal to log n to the base 2. So, 8 means 2 power 3, m is equal to 3 stage. So, n is equal to 8 now. So, log 2, n is equal to 8, 2 power 3. So, you can write m is equal to 3. So, m equal to 3, number of stages, 3 stages. Therefore, the total number of complex multiplications will be the total number of complex multiplications will be n by 2 log n to the base 2, and the complex additions are multiplications and additions are n log n to the base 2. The total number of complex multiplications n by 2 log n to the base 2. Okay. So, once the butterfly operation is performed on a pair of complex numbers a comma b to produce a comma b, once the butterfly operation is performed, okay. So, here if you see, just a minute, power. Actually, okay, we'll continue. So, in this, once the butterfly operation is performed on a pair of complex numbers, the complex numbers a and b, to produce the complex number, this is also complex number, to produce the complex capital A comma b, that is a and b complex numbers in this basic butterfly structure. If you compare the two complex numbers, okay, then there is no need to save the input pair a and b again. We can store the result in a and b itself, the same location, the result a and b, okay. There is no need to save the input pair a and b. The result a and b can be stored in the same locations. So, overall only 2n storage registers are required. 2n storage. So, n is 8 means 2 into 8, 16 is equal to 16. 2n storage registers are required for endpoint DFT, for endpoint DFT, so that the computations are done in place. So, in place algorithm, so that the computations, normally we say the computations are done in place by storing in place. Normally we used to say in place. Computations are done in place. The computations are The computation are carried out separately. The computations are carried out separately, even indexed and odd indexed samples to reduce the computation effort, but all algorithms allocate the storage for computer results. So, the less storage is required means the more efficient is the algorithm. So, many FFT algorithms reduce the storage requirements by performing the computations in place, by storing the results in the same memory locations that previously hold the data. Okay, so this is a in place concept. So, butterfly structure. So, in this session, so completely we have the complete fundamental concepts of FFT, decimation in time algorithm, radix 2 algorithm. So, what is FFT, how the algorithm is developed, what is the relationship between the number of samples and the base R, radix 2 and radix 4, and how it is decimated into odd and even sequences. So, similar way, by using the symmetry property, how the x of k is repeated, it is a symmetry property w of n by 2 plus k is equal to minus wk. Using this property, how is decimated, how the even sequence is even and odd, again even is divided into even and odd is divided into even and odd. So, complete derivation we have seen, and how it is the decomposition will be done until you get 2-point DFT is obtained, and what about the number of butterflies in each stage, how many stages, and the basic 2-point basic butterfly computation, because this computation only required for each stage, how the two complex numbers a b used to compute the two complex, how it produces the two complex numbers a and b, the one multiplication, the two complex additions, and how many stages are required, number of stages required to compute n-point DFT, in each stage how many butterflies are required, n by 2 butterflies are required, totally how many multiplications and additions are required, total number of and additions are required for this. So, next session we will discuss about the complete 8-point butterfly structure, and we will take some example how to compute 8-point decimation in time FFT and decimation in frequency FFT algorithms, and IDFT and endpoint DFT, in decimation time, decimation frequency, the complete butterfly structure will see, and we will take some examples to solve the problems. Okay. So, this session is very much required to understand the FFT DIT algorithms in order to compute for further problems. Okay. Thank you.